Hello everyone. Let's do one more numerical on de Broglie wavelength. Okay, so suppose we have an electron whose de Broglie wavelength is of the order of 1 angstrom. So it is written here. So 1 angstrom is 10 to the power minus 10 meters. What would be the velocity of electron? So we have to find out the velocity of electron. Okay, so velocity can be given as distance upon time, right? Okay, and how long would it take the electron to make one round on its orbit around hydrogen nucleus? Okay, so we are talking about hydrogen nucleus. So hydrogen nucleus, actually it is on its orbit around hydrogen nucleus. So these are the atom is hydrogen, and we have to consider the length of its orbit. So orbit length would be 2 pi into r, where r for hydrogen atom is about 5.3 into 10 raised to power minus 11 meters, that is 0.53 angstrom. Okay, so we are going to use this is going to be the distance that electron is going to cover. The distance would be about 10.6 into pi. So 10.6 into pi, 10.6 into pi into 10 raised to power minus 11 meter would be the distance. Okay, so we have to get the time. So time can be given as distance by velocity. So we can see that first we have to find out the velocity, and we do have the distance now. So time would be distance by velocity. Okay, so how to go about it? Okay, so we have been given lambda of 1 angstrom, and that is for electron. So we know that lambda of electron is given by h upon momentum of electron. Okay, so momentum, therefore the momentum of electron can be obtained by h upon lambda of electron. Okay, so and this momentum can be written as mass of electron into velocity of electron. Okay, so this is the point from where we know that we can solve the question now. So we have to find out the velocity of electron. So it can be given as h upon lambda, and this mass will come down. So mass will be here. Okay, so this is the velocity that we wanted to obtain, and the time that we want to obtain is given by now as distance is 10.6 into pi. So 10.6 into 3.14 into 10 raised to power minus 11 upon this, that is the distance, upon velocity, which whatever we are going to obtain from here. So this is 6.6 into 10 raised to power minus 34, that is our h. And lambda is given as 1 angstrom, so it is 10 to the power minus 10 into mass of electron is 9.1 into 10 raised to power minus 31. So 9 into 10 raised to minus 31 would do. Okay, so whatever we get from here, from this velocity calculation, it has to come down here, right? So we will calculate it first. So velocity, okay, I will change the color now. I'll take yellow color. Okay, so we have velocity equals 6.6 into 10 raised to power minus 34, and this is 10 raised to power minus 31, and this is 10 raised to power minus. So I will first take care of the powers. So 10 raised to power minus 34. This minus 10 will come up plus 10, and this minus 31 will come up plus 31. Okay, and we have here 6.6 by 9. Okay, so velocity is going to come out as 9 7 is 63, so it is about 0.7. Okay, this is approximate answer. You can calculate it exactly with your calculator. And this is 10 raised to power minus 34 plus 31 is minus 3, and plus 10 is plus 7. Okay, so this velocity has come out to be velocity is about 7 into 10 raised to power 6 meters per second. So 7 million meters per second. Okay, now we are going to put it here. So time would come out to be 10.6 into 3.14. So I can take it as 11 into 3. Yeah, so it will be about 33 by 7 into 10 raised to power minus 11, and this 6 will come up and become minus 6. So time will be approximately 7, you can take it as almost 5 into 10 raised to power minus 17 seconds. So this is very high speed. This is very high speed. So the time taken would be very small. So for an electron having a de Broglie wavelength of about lambda of 10 raised to power minus 10 meter, that is 1 angstrom, velocity is of the order of 10 raised to power 6 meter per second, and time around its orbit, time for one revolution around its orbit is of the order of 10 to power minus 17 seconds. So you can see that if you apply de Broglie's wavelength for atomic unit, that is for electrons or atoms, you get reasonably good answer, right? Okay, so that was the point behind this numerical. Okay, thank you.